In this video, we look at Advanced Higher Biology, Unit 3, Investigative Biology, specifically the key area 2A and B, so pilot studies and experimental design. In the video, we look at the pilot study stage, so we look at why they're carried out and how they form the experimental method. We'll discuss how variables can be independent or dependent. We'll look at continuous and discrete data, explain why placebos might be used, what the placebo effect itself is. We'll suggest how an experimental design can be altered to deal with confounding variables, and how experiments can be either simple or multifactorial. We'll discuss differences between observational experimental approaches, and how in vitro and in vivo studies differ. Some general terminology. When designing experiments, we as researchers must ensure that variables which could affect the results of the experiment, so-called confounding variables, are controlled so that any measured effect is likely to be due to the independent variable. An experiment would only be considered valid if all concentrations, volumes, masses, and demographic factors, for example, that weren't the independent variable had been completely controlled between the different groups. In terms of reliability, we are ensuring that we carry out our investigation. We include both repeat and replicate measurements, and that these give us consistent results when compared with an experimental group. Both terms refer to taking multiple measurements when using the same combination of factors and while controlling the confounding variables to ensure validity. It repeats. The measurements are taken during the same experimental run, so we can use the same dishes for Petri dishes, we can use the same stock solutions and the same setup for equipment. A truly independent replicate must occur with the same conditions but using completely new media, organisms, solutions, environment. In this way we can ensure that any unidentified confounding factor hasn't influenced the results. Accuracy. Simply put, when data is accurate, it reflects the true value of the measured variable. Accuracy is relevant not only to the raw data, but to when we calculate our means also. And finally, precision. Slightly different to accuracy, precision measures how closely grouped the measured values are to each other. It's possible to get a completely inaccurate reading, but be very confident that you're getting a precise one. So the results always come out pretty much the same, but it's the wrong result. Pilot studies. Integral to the development of the investigation, a pilot study is used to help plan procedures, assess validity, and check techniques. Especially when you're using an unfamiliar protocol or organism, it's important to find the most appropriate volumes, temperatures, and any other variables to use in your particular experiment. Trial and error allows evaluation and modification of the experimental design. So the use of a pilot study can ensure an appropriate range of values for the independent variable. For example, in an experiment examining the effect of different wavelengths of light on plant growth, a pilot study might give an indication of a rough lower and upper effective threshold, or may, if you'll excuse the pun, illuminate safety or financial issues when using high quantities of dangerous chemicals. In addition, it allows the investigator to establish the number of repeat measurements required to give a representative value for each independent datum point prior to a large-scale investigation. So it'll ensure you get concurrent results. In the full experimentation phase, we have to have an independent variable, which is the one manipulated by the researcher in the experiment. It's also the X variable. So when we have a good aim, we would find the effect of X on Y. So we're looking at the effect of the independent variable, say temperature, on the dependent variable, which is one we're measuring. So that's the Y variable. So if it was to find the effect of temperature on enzyme activity, X, the independent, is temperature, Y, the enzyme activity, is dependent. The independent and dependent variables can be continuous, which quantitative data which can be measured and has an infinite possible number of values within a given range, or discrete, which possible number of values in which the data can be categorized and easily counted. To make conclusions, the experimental treatment group is compared to a control group, When designing studies, they can either be simple, in which only a single independent variable is examined, or they can be multifactorial, in which several independent variables are examined. A simple design allows you to control most confounding factors, and it's easy to achieve in a lab setting, much so more so than in the field. Whilst there's more control, a drawback of a simple experiment is that its findings might not be applicable to the wider setting. Biology is quite complicated, and in nature there's often many different factors which together affect the dependent variable which you're measuring. There's a classic joke in biology where a farmer asks a team of physicists to improve the milk production of his cows. After a month, they come back to him and say they can easily double the cow's milk production, for free even, but we have to assume that the cows are spherical and in a vacuum. So what the physicists have done is they've completely controlled the experiment and removed a lot of very important other factors. This shows how limited the impact of these simple investigations can sometimes be. A multifactorial experiment is often more generalizable because you're using several different independent factors, but is less valid and reliable. At times, investigators may need to use groups that already exist rather than making their own. For example, a pack of wildebeest that already exists in the wild. In these studies, there's no truly independent variable, and researchers will often just not make active changes to the group and just conduct an observational trial or study. In the observational study, the independent variable is not directly controlled by the investigator, either for ethical or logistical reasons. So it either shouldn't be done because it's unethical or can't be done. These observational studies are quite good at detecting correlation, but since you don't directly test a hypothesis, it's quite difficult to get causation. In terms of correlation with causation, it's covered in a future video. But data can often look to give a correlation in which it seems to be that there's an observable relationship where a change in one variable seems to map with a change in another. This doesn't necessarily mean one is affecting or causing the change in the other. For example, the number of people you've met in your life and the number of times you've read a sentence probably correlate positively. But this is just because in both cases, as you get older, you'll meet more people and you'll read more things. So both will increase with age, although one is not directly affecting the other. In the same way that, in this graph, your per capita cheese consumption and the number of people who die tangled in their bed sheets, it may have an incredibly good correlation, but they're not related. It's coincidental. The divorce rate in Maine apparently really nicely, 99.26%, correlates with the margarine consumption in Maine, but seems to be a coincidence. The letters in the winning World of Scripts National Spelling Bee and the number of people killed by venomous spiders, again, a decent correlation. Due to the complexities of biological systems, other variables beside the independent variable may affect the dependent. In simple studies, it's often easy to control these, and they're called confounding variables. They must be held constant if possible, or at least monitored so their effect on the results can be accounted for in the statistics. In cases where the confounding variables can't be controlled, a randomized block design could be used. The randomized blocks of treatment and control groups could be distributed in such a way that the influence of any uncontrollable confounding variable is likely to be the same across both groups. In this example, a new drug has been developed which is treating a respiratory illness, and they've got people who smoke and people who don't smoke, males and females, in to be their subjects. You can see this is a poor design, this initial one, because all the men, smokers and non-smokers, are getting the drug, and all the women, unfortunately, do not get the drug. In the second example, it's different, but it's still bad. It looks like now all the smokers, males or females, get the drug, and again, the placebo group in this case is the non-smokers. Non-smokers. The third one is devious, and they look like they've done a proper randomized block design, but if you count the number of black squares, which is male smokers, there are seven on the left and only 5 on the right, which isn't really fair. Whereas in the final example B, you can see there's an equal number of male smokers, female smokers in each group. Control results are quite often used for comparison with the results of a treatment group. So a negative control provides results in a complete absence of the treatment. It's what, going up through the school, you'll usually have used as a control. The positive control is a treatment that is included to check that the system can even detect a positive result when it occurs. In the case of a pregnancy test, there is a positive but not a negative control. The first line is a positive control, as it should always appear. If it doesn't appear, it suggests that your test will not reliably pick up a positive result or cannot. If there was negative control, it would be one where there was a strip of material which should never change colour. And if it did, it would suggest that your test has been faultily either designed or manufactured. Placebos. Placebos can be included as a treatment without the presence of an independent variable being investigated. So it's very close to the definition for the negative control. The placebo effect is a measurable change in the dependent variable as a result of a patient's expectations, rather than actually as a result of the change in the independent variable. In some experiments, a negative control can be used to examine the placebo effect. Finally, we look at in vivo versus in vitro. So, in vitro refers to the technique of performing a given procedure in a controlled environment outside of a living organism. For example, within the cells growing in a tissue culture, in proteins in solution, or in purified cell organelles. An easy way to remember it, I find, is that IVF, test tube babies, in vitro fertilization occurs outside the body. Normal fertilization would occur inside the body and would be in vivo, which refers to experimentation using a whole, live, in situ organism. While in vivo experiments are more realistic of natural conditions, they're more difficult to control and replicate. It's very difficult to get exactly the same thing to happen every time. In the video, we covered Unit 3, Key Area 2, A and B, so pilot study and experimentation respectively. The next video completes this key area and discusses sections C, sampling techniques, D, reliability, and E, presentation of data.